Hi Aaron, hi Fatima.
Of course, they don't take cards. Why would they? What is this? Got a nickel. No, I'm determined this is gonna work. I got some pepper spray. Look at that. Let's see if I can get it. I don't think they accept pennies. I think they accept everything but pennies.
We'll give you a quarter.
Oh my gosh, thank you. Alright, I will be back.
Do you see slides?
We see him.
Okay. I probably need to make sure that we don't have backup sound. Aaron?
Yep.
Do any of you see the remote?
Yeah, 1 second.
Can you do a little zoom out? Excellent. And yes, a little bit more. Perfect. Maybe, yeah. Excellent. Many thanks to Daniel for preparing his slides, and I will cover a couple of issues. We may have different attendance in and out here, most likely in, and okay, yeah, the noise is less. So I cannot speak for second part of the group from Dr. Kivinen, so I will do overview of research at our part of the group, and then remind about ACS in Boston. Many of you may plan to go there, and then do research overview of research in perovskite that we do in Fargo. There is also very active research here in Los Alamos, but we do a little different things. And many of us, including Fatima, who is here, and Landon Johnson, who has some schedule conflict, are starting non-collinear speed calculations. I'm going to cover it a little bit, and then we'll briefly show the presentation that was presented on the recent ESP conference that was prepared by Aaron and presented by myself. And then there will be time for second part, research update by Daniel. Okay, so please stop me or remind me if I speak longer than an hour. I'll try to I'll try to be quick, and or stop me if I'm going too quick and too fast and it is not comprehensible. So it is what we are doing. There are two pending grants that if any of them will come through, we will live richer, better. Do you see? Oh yes, they see. Since January, and basically what I'm showing, it is application for additional NERSC hours. We are close to expire the generous gift of 6 million hours that we received in May. And I'm requesting another 6 million and trying to tell that we are super productive, that since January we have 5 published papers. If John is listening, his work is important here. So vacancies, Los Alamos ACS energies, and then Yulun on lanthanide spin orbit emission. Then the collective paper started by Brandon on nanotubes, and there is a paper leftovers from South Dakota about transition metal doping to titanium dioxide. And we do have 5 papers submitted. You recognize Aaron, Yulun, and Fatima comes twice, and Aaron comes twice in submitted papers. There will be 2 papers to be submitted within a week, and there are several active projects that may or may not result in papers by the end of the year. And if you do not find yourself here, it means you are likely part of Professor Kivina group. Also, there were a couple of presentations based on this DOE support at Excited States, at Sunnyvale and Materials Research Society, and I'm done with the first part. So the goal was to give a brief update and to give credit to authors of these works. Questions? No questions. We'll go further. So I was lazy to do step-by-step show. It is on the last page, but there is a time limit for discount registration. So you may consider to go and register. And if you do membership, before doing this, make sure that whoever is your advisor is agreed to sponsor your travel. Do not do it on your own and then come up like, I don't know, I want my development, it's your responsibility to pay for me. But most of you are going. So the registration is reimbursable, but membership fee is not. So it is for students, it is not very big, but consider it's about $100 your investment in membership. And some of you have already made steps towards lodging and travel. And if you didn't, well, the best way is to find a big house and live all together. It will be super least expensive than hotels. But if you, by some reasons, need hotels, the ACS give some discount hotels which you can go by the link only after you register. The link is not available if you just browse the web page. And some quick people have already used this opportunity. I already have a reservation, just showing what was last night. So they have something in the vicinity of the Boston Convention Center. And if you stay just nearby, it will be like a little below 300 per night. And if one is ready to drive or walk for a couple of miles, then it will be affordable. And especially if sharing. So here are the examples of what is available, and some of them have continuous days available, some of them are not. Okay, done on ACS Boston. Research, I will be quicker than an hour, likely. So research on perovskites in North Dakota. So there are several active and talented researchers who are in the room in Fargo and who do research, and the directions can be approximately split according to dimensionality criteria. So there was a lot of research on bulk perovskites by John and Yuwoon in the past, and right now we do have thin film surfaces, one-dimensional nanowires, and zero-dimensional quantum dots, and all of them exhibits several challenges that are often interconnected in each of the directions. One of the motif that is shared in all dimensionalities is surface ligands, same as part of our community who do quantum dots. So their uncovered, untreated surface is able to be active in surface traps and be disabled for useful engineering applications such as charge transfer or light emitting. And placing right ligands at the right places on the surface make material much more useful for any of dimensions. So one of the projects, I skip photographs and names, but I will add them if it will be presented later. So this is credit of Dr. Yuwoon Han. This is the work that is about to be completed in maybe a few hours. Collaboration with Dr. Uwe Burghaus, where the very simple molecule is adsorbed on the surface of lead halide perovskite, carbon dioxide, and then by some reason it shows it binds much firmer than to any other material. And their challenges for this surface chemistry is that presence or absence of defects may, in addition, affect conductivity of the material. So it may enable sensor applications. The generally studying of binding pattern of ligands can be later forwarded to studies of the colloidal nanostructure to design right ligands and understand their binding patterns. And also there is a unresolved question. The perovskites, I'm skipping the introduction, but they are inorganic scaffolds with either organic or inorganic cations that can either translate or rotate inside. And this is very much polarizable material with dielectric constant. In bad perovskites it's 100, in good perovskites it's above 1000. So they're very polarizable, and depending on the polarization, internal polarization, the binding energy can be also affected. So in this little work, the carbon dioxide binds with residual water on the surface, forms the bicarbonates such as in the soda drinks, and then it firms tightly because this hydronium and bicarbonate ions replace natural anions and cations of perovskite, and Coulomb electrostatic holds them really strong until one heats the sample up until noticeable temperature. So another research that we hope will be updated today by Daniel Ramirez deals with flat surfaces for photovoltaics applications, where the rough surface without ligands or with wrong ligands may have affinity for surface defect, surface traps, and be not applicable for applications. So there is a ongoing research of finding pairs of anion and cation ligands that would match the crystallographic symmetry of original perovskite, hold there tightly due to electrostatics, and push charge carriers, electrons and holes, inside the perovskite. The preliminary data which I have, and probably today we will learn more from Daniel, that if one doesn't use pairwise ligands, but only one of them, either one, then they will work either as p doping or n doping of the material. But if they both, it returns the material to the intrinsic configuration. There is also important part that no one of us has researched, but it is a part that was already published in Nature a month ago by Alexander Efres, and he bragged about it on the conference, that if one, most of the perovskite nanostructures match the cubic symmetry, and nanostructures have also orthogonal coordinates, and concept of the particle in the box that most of us take in at the very beginning of quantum class applies very well, and allows to reproduce electronic structure, density of states and spectra of perovskite nanostructures. So right now it is not assigned, but each of us can, or at least few of us can try this direction, and it may give fruitful results at a no time. Only one paper has been published on this, and typically one paper in strong journal like Nature is followed up by a horde of like 50 papers of above average journals. So there is place in this area of research to put our feet into the door. So one-dimensional perovskites currently pursued by Fatima. So her preliminary research and her work is also contributed by suggestions and help from collaborative help from John and Yulun, and maybe Aaron, I don't know, teamwork. But Fatima is a main expert in one-dimensional nanostructure. So the problem that we face, not only for perovskites but for any materials that we model, is that the radiative, optical, and non-radiative lattice vibration-induced processes in dynamic processes in materials can be affected by so-called k-vector, by momentum. So if you were taking computational class, or if you were doing solids, I know Jabet makes similar research for lead selenide nanoplatelets. So the set of electronic orbitals may have non-zero net momentum, and depending on this net momentum, the electronic properties of sets of orbitals and abilities to absorb light or to interact with lattice vibrations are different. And there are two types of transitions: direct, when the momentum is conserved, and indirect, when initial and final state have different electronic momentum. This is very novel research direction. It needs a lot of coding and debugging, but this may bring healthy benefits. So we may want to mimic or model conservation of momentum, where the difference of momentum of electronic state before and after interaction is left away with momentum of the system of nuclei. This is challenging because we are based on molecular dynamics rather than normal modes with enabled momentum analysis. But what we can do, and here I see connection to time-dependent excited state molecular dynamics that is controlled and pursued by Dr. Han. The research on one-dimensional nanowires can be tested in the following direction. One can practice same philosophy as one does for TD-SMD, creating several in-cars with different Fermi excitations. And in addition, one can create several k-points files. So at each time step of trajectory, the script parses the right Fermi configuration, right k-point configurations, and then continues the dynamics. And then the motion of nuclei will be changed depending on value of electronic momentum. Maybe we can achieve practically important results without this calculation, but it is a last resort. If nothing else will help, if calculations will diverge from experiment, this method, this approach should help. So there is a lot of unknown, interesting things in this area. And you see this little figure, it is what one would like to obtain. If one excites at non-zero k vector and one has only HOMO and LUMO, it doesn't stay at the original momentum, but it jumps down to gamma point or whatever minimum in the dispersion law is for both electrons and holes. So it is the basic process that we do want to mimic. So little incremental indirect transition with loss of momentum into lattice vibrations. So London is not only the capital of Great Britain, but also a member of our group. And he's also looking on the flat two-dimensional thin films of perovskites, but he has them functionalized with different materials. Similar project was successfully processed and completed by Aaron in the past, but the idea is, that if we are looking not to a basic science but to applications, do you see the mouse? Yes? Okay.
Yes, we are.
Okay. Excellent, excellent. I know that there are ways in PowerPoint to make a much bigger marker or flashlight, but I need to learn it. So the perovskite material is sandwiched between additional functional materials layers. So in addition to anode and cathode, it needs electron transfer media and hole transfer media that would pull charge carriers, electrons and holes away from the perovskite when it has been, these carriers have been photogenerated by excitation. And Aaron has successfully completed research of the hole transfer from perovskite to spiral-omitted molecule or substitution of spiral-omitted. And right now, I hope London is continuing research on the electron transfer from perovskite to electron transfer media to titanium dioxide. When I will return to Fargo, I'll check if there are actual developments in this. But this research has several fundamental and practical challenges. So the figure on the right is focused on this perovskite and ETM layers, perovskite and ETM, and the main question in this design of interfaces is the correct alignment of energies of bands. Because in order to drive charge carrier through the interface, one needs to have difference of potentials, electrostatic force, and difference of potentials is related to energies of LUMO at one and another material if it is for electron transfer, and energy of HOMO at one and another material if it is hole transfer. So in the favorable alignment of bands, a photoexcitation, number one, results either in relaxation of electron in the conduction band or charge transfer to the conduction band of the interfacing titanium dioxide. And then, upon this relaxation, due to difference in potential, the electron will anyway jump to the titanium dioxide, and the lowest excitation will be a charge-separated state when the hole stays on perovskite and the electron resides on the titanium dioxide. So the question for research is to investigate if the morphological parameters of the simulation cell affect alignment of bands, first. Second, if morphological parameters affect the height of barrier and couplings and ability of electron, the rate how quick it transfers. So here the figure on the left shows favorable alignment that I just shown, and figure on the right shows unfavorable alignment. So here the LUMO of the titanium dioxide is slightly higher than LUMO of the perovskite. In this alignment, the transfer will happen, but it will not stable. It will be very short-living. Upon charge transfer, it will come to lowest available excitation will be intrinsic perovskite HOMO to LUMO. So this alignment, even without computing any dynamics, will be unfavorable for charge transfer for photovoltaic applications. And there are several things, including ligands, size, crystallographic phase, doping, that affect this mutual alignment. And sometimes, well, very general trends can be done by putting oxidating or reducing agent, but fine-tuning is hard to predict without calculations. Therefore, ab initio modeling is needed. Okay, and now we are coming to zero-dimensional, which has least amount of dimension but largest amount of challenges. So, if you are interested in zero-dimensional nanostructures, perovskites, please follow me. If you are not, just lean back and relax for a minute or two or more. So, generally, when you will present in public, you can always tell that I am studying structure-to-property relations, right? This is very general. It doesn't mean anything, but it is correct. So we are changing atomistic models, and we are getting properties of materials that we model. So the structural factors can be considered as confinement, presence of different ligands, temperature and thermal motion, presence of vacancies, doping, and presence of nuclear reorganization, which means upon excitation the geometry slightly changes. And the properties, I'm not telling observables, we are too far from predicting observables immediately, but general directions for properties is electronic structure, ability to absorb light, ability to dissipate energy through lattice vibrations, non-radiative processes, charge transfer, emit light as photoluminescence, and ability to generate more than 2 electron-hole pairs out of one photon, so-called multiple exciton generation. And here are the very rough, intuitive ideas how each of the structural factors can affect properties. So if you plan, if you plan to write introduction to your paper or a thesis, you may put something like this. Maybe not as table, but more like words. What is expected before you report results? So confinement, which means your piece of semiconductor is smaller than bulk, may increase gaps and subgaps, induce blue shift in absorption, slow down relaxation, change direction of charge transfer because it changes alignment, as we discussed for London project, makes also blue shift for photoluminescence, and confinement is a key factor for multiple exciton generation. Without confinement, it is a very inefficient process. Ligands are expected to remove trap, facilitate radiative absorption because they push charge carriers inside nanostructure. They speed up non-radiative relaxation because they add additional degrees of freedom with different frequencies. For charge transfer, they may serve as linkers. And for photoluminescence, they also favorable because they remove traps. Nothing for the rest of structural factors, nothing is known for multiple energy generation because it is extremely expensive calculation for about a year of, or maybe half year in most favorable case for a single model. So thermal motion is expected to elongate chemical bonds, and it affects spectra by adding thermal broadening, and also elongation of bonds may induce blinking. For non-radiative relaxation, thermal motion is a key factor because at 0 K, the non-radiative relaxation is vanishing. For charge transfer, the motion of nuclei provides irreversibility. So if it did transfer, it didn't transfer back up in energy. For photoluminescence, it's also adds broadening and effect of blinking, which is unfavorable. Vacancies happens, they create traps, and they typically unfavorable for conductivity, for absorption of light. For non-radiative relaxation, they create traps, and for relaxation is typically slowed down, but recombination sometimes goes quicker on trapped sites. And this same is correct for doping. For charge transfer, the traps and doping may tune alignment of bands, which is a good plus, but it may trap charge and prevent it from being transferred, which is negative. And for photoluminescence, vacancies typically quench, forbid it, but intellectually chosen doping may stabilize and help luminescence. For nuclear reorganization, optical properties do reflect so-called Stokes shift, that absorption and emission happen at different frequencies, and for non-radiative relaxation is slower, and charge transfer is typically slower due to Marcus mechanism. 35 minutes. Okay, and I have heard that the challenge of spin-orbit couplings is being distributed and penetrating through the group. The spin-orbit, or more generally non-collinear spin approach, is a big waste of time. If you predominantly know that your model is closed shell and you have hydrocarbons or first row elements, just skip it. It will save you a lot of compute hours and will help you to achieve goals quicker. But for some models, it is unavoidable. And if you already desperate to do something magnetic, then non-collinear is more general than spin polarized. So it is summer. We shouldn't write too much equations as a relaxation. So, but I'll show some cartoons how to interpret the spin orbit and what to expect if you suddenly decide to jump into it. So, in case you have closed shell, no spin polarization, you have, and suppose, let's focus on conduction band. So you have some orbitals, right? No spin degree of freedom. If you have spin polarization for first row transition metals, you will have same indices of orbitals, but they will be for spin up and spin down, alpha and beta, right? And suppose that there is no spin orbit coupling. We are talking only about basis. There is no spin orbit coupling, but there is a non-collinear spin basis. Then total number of orbitals is 6 as for spin polarized, but they are counted in a continuous way. So whatever was LUMO for beta is LUMO for non-collinear, whatever was LUMO for alpha is LUMO plus 1 non-collinear, and then it goes 1, 2, 3, 4, 5, 5, total 6. So we can survive it. But in addition to electronic structure, we also have transitions, optical and non-radiative, right? And it is expected that if there are larger count of orbitals, there is a larger count of transitions. So those transitions are qualitatively different. And some of them were not available if you do not include non-collinear spin treatment. So let's look on the left. If we didn't have any spin, closed shell, we have only 3 transitions, plus opposite direction, right? So total 6. And matrix 3 by 3, and diagonal do not count when particle stays at the same orbital. If you do have spin polarization, you have similar transitions, going down 1, 2, 3. For alpha, going down 1, 2, from 2 to 1, 1 to 0, and 2 to 0, right? So total 6 transitions. But if you are going to non-collinear spin, we will have the same transitions from the former alpha to former alpha, 3 transitions, blue color here, then pink, former beta to former beta, another 3 transitions. But it is not the whole story. Those were spin conserving transitions when the spin projection doesn't change. In addition, there are transitions from pink to magenta, cyan to magenta. And they can go either from this cyan to magenta, that's 3. I'm skipping the degenerate states, and light green. Then there are transitions from magenta to cyan, also 3, these dark green transitions. So we already have 12 transitions. And in addition, these little yellow things, they are spin flip, spin forbidden transitions between states that before introduction of spin were having the same spatial symmetry. So it's keeping the same spatial orbital, but just flip spin. And they can take very large values, but if there is no actual spin orbit coupling, they will not change the energy. So this pink and cyan are degenerate. So total, how many? 15 transitions. So once again, well, first I did the final figure, but I understood that I cannot understand it. Therefore, I'm trying to introduce it in slower fashion. So the transitions from alpha to beta, from cyan to pink, and transitions from beta to alpha, from pink to cyan. We also have to exclude diagonals, but because it stays at the same place. In addition, we have light green for spin forbidden transitions originating from alpha, and dark green spin forbidden transitions originating from beta. In addition, plus 3 transitions between degenerate states. And if we summarize this all together, here are all transitions. This is not specific to any system. It's just arbitrary 3 levels with spin degree of freedom. And here are possible transitions. So if you decide to include spin orbit coupling, and if your software allows it, be ready to face the complications. Instead of 3 transitions, you will analyze 15. So Aaron has already done it a couple of times, and he still survived. So, which means a human being can do it. Okay, done with challenge of non-collinear spin, still within 1 hour, and let me share. I would be happy to share notes that I did during presentations of others, but it would take much longer time. So I'll share only my presentation, and I'll skip details and show only movies to entertain you, on the record that it is summer and it shouldn't be boring. So there are different dimensionalities, vacancies, transitions, but we will focus on magnetic doped quantum dot, which is expected to give photoluminescence. And here are credits to.
Hey, are we done? Are you done? We are too late.
No, you skipped most interesting part.
The most interesting.
And now you'll see what you have already seen.
Oh, okay.
So
I will give back a couple of slides back for Levi and Professor Kilina.
can they see it?
Yes,
It shows like
Yeah,
no
it
video.
shows
they
no
do.
video.
They do. So we just
They can see there's no video.
they can. If you look to the upper right corner, it shows the screen that we have, and the very upper right, our smiling faces. So if you do have spin orbit transitions, there are between 3 orbitals. Instead of 3 transitions, there will be 15. Just
Due to the spin orbit coupling.
even without spin orbit coupling, if you use non-collinear spin basis. So if you decide you need it, be brave. And I'm going to skim through slides.
But your non-collinear,
Yes?
not necessarily that you will have your alpha and beta spins being splitted. You might have
Yes.
degenerate states, and
Yes.
then there's no transitions, of course, if you have the same energy between your alpha and beta.
But in your basis, the states will be present.
right?
We are not.
But you
We are
will
not speaking
have
about.
15
We are not speaking
transitions.
about intensity of these transitions. We are talking about number. So you just matrices will,
But if your states are degenerate, there's no transitions between degenerate states.
or it will be like predominantly split, superposition of both. Okay, I'm going to quickly go through slides that I was showing in Santa Fe, because there are some movies. So we are looking on magnetically doped perovskite quantum dot, which is expected to give stable luminescence when the the ligands on the surface may experience elongation of bonds due to thermal motion and then quench luminescence, while the magnetic doping inside will be not affected by this feature. So we are using density metrics with non-adiabatic couplings, and here are the equations for non-collinear framework. So each orbital is replaced by alpha and beta component, which are not independent. And here are the rates for optical and non-radiative transitions. So
You promised movies.
movies, yes, yes, there will be movies. So this is figure prepared by Aaron showing the summary.
They are so bored that now
No,
they're talking between each other.
no, it is good. It means the healthy scientific environment when everyone is arguing. We should start arguing between us as well. Or we can call Alice and Jabet and interrupt them.
They cannot hear us?
They can.
They can see but not hear.
No, they can hear, but they probably discuss something important.
Well, you can call just by name. They should really recognize their names.
No, it is something really important. You can listen to them.
I'm just curious, what other people are doing there?
Hopefully listening. So here is
I
the.
just have a question. Guys, do you hear Dmitry?
Yep. Yes.
Good?
See?
Yeah, really? Because we now start talking between each other and...
That's fun.
Yeah, it was fun, yeah, but looks like no one was complaining.
We were not complaining when they talked to each other. I was not. So
Movies.
if you will be, if you photoexcite this perovskite valence and conduction band, there could be several processes. There could be intrinsic emission, there can be trap to surface traps, or there could be emission from states contributed by doping. And here is the model that Aaron has put together, and here is how it looks like.
This is video?
There
This
will
is
be-
just rotation. It's not a movie.
Yes, but it is
It is a movie. It's a.
It is
It's a fake movie.
it's 20
It's
megabytes.
just moving to show
Still-
the structure. This is not a movie.
Well, you have a demanding audience.
Something Xavier.
No, you have a demanding audience.
I thought you show the dynamics.
You will see it. There will be
Or
dynamics.
like appearing of your charges, kind of, you know.
You have
real.
seen it. You know what to expect.
I didn't see it as a final product.
So there is a slightly distorted cubic structure. This cyan spheres are cesium cations, and in the center there is a manganese doping. And this shell of anion and cation ligands push charge carriers inside and prevent formation of trap states. Okay, skipping. There are
Absorption.
yes influence
What's the
on
difference between green and red?
with and without spin orbit.
Oh,
Spin-
I know.
spin
This
orbit-
is the result of Erin from
Yes.
his poster. I recognize it.
So spin orbit gives redshift, substantial redshift, and then it gets comparable to experiment. In presence of magnetic doping, there are spin forbidden transitions that were not available without spin orbit and that appear in this red area of the spectrum. And so by demand movies. So thermal motion is a reason for violation of orthogonality between orbitals. So orbitals before and after some delta t time are not orthogonal, and it gives rise to probability of transition between these orbitals. And we can plug in these so-called non-adiabatic couplings and run for electron dissipative dynamics, where these rates allow electronic energy to be dissipated to lattice and slowly jump from more excited to less excited states. And you see that organic ligands are more vivid in motion than this heavy bromine, lead, and cesium. And some of them form hydrogen bonds to each other, but it is very, very dynamic and
This is actually was a kind of comment, I guess,
Yes.
to Daniel, right? Daniel, right?
Daniel, yes.
When he was presenting his results for the computational course, right? Like we were suggesting that there are formation of hydrogen bond, and Ken said like if you have anion and cation, and this is what you have for your systems, then it should be just the regular Coulomb interaction between positive and negative charge. It's not really hydrogen bond. It's just static electric
Well,
interactions.
this acetic acid is deprotonated. So these oxygens are very hungry to establish friendship with anyone.
Yes, but I think what Svetlana is saying is the definition of hydrogen bonding does not mean this. This is just
Well, it
like
might. No,
dipole.
it might be really hydrogen bond formation rather than just
Okay.
interaction between plus and minus.
Let's put it
charges.
this way. Oxygen from this carboxylic group and hydrogen from amine group.
So it's an amine. not-
Yes, yes,
Okay.
it is. Cation. Come to the distance.
Amine is neutral. What do you mean it's cation?
Ammonium.
Ah,
Oh, and it,
Ammonium.
so they're
Ammonium.
both charged.
Both
yeah,
charged.
that's exactly the
Yeah,
point.
yeah.
Cation
But
and
they are
anion.
coming to such distance, which would correspond to
the hydrogen
hydrogen
bond.
bond.
Okay.
I'm not saying that it is hydrogen bond, but it is a distance that would correspond to hydrogen bond.
Okay.
Okay? And then
Now we know what to answer to Ken.
let's call him right away.
Well, it's work of Daniel, I guess. We should.
Daniel, call to Kent, Dr. Rogers.
And tell that now you know the answer to his question.
Do you have anything
Okay, but Daniel, you are welcome, or how to say, you are encouraged to do movies like this. Okay?
I would put it like you are required.
No. What should I do if he declines?
Uh,
No.
We had a reviewer on a paper that we were submitting to what I did last time, and they're like, you should put videos of your dynamics in the supplemental.
But is it like demanding or just
Did you? Well,
opportunity?
for reviewers, usually you better try to please them.
It's not due until the 20th.
Okay.
But are you planning to?
So, what happens to energy of excitation?
Yeah.
Well, we'll go to the movies. But first, I want to show this result of Aaron with this degeneracy that you pointed out. So, if there are states that are almost same in energy,
But in your case, you have non-even number of electrons, right? Or like you have.
there are two
Closed
cases.
shell
There
or
are two
not closed
cases.
shell?
So, this one is closed shell and the upper, and lower is open shell.
Or when it's doped.
Yes.
This is for spinel opening?
Yes, everything for spin orbit. So,
But so this is no doping. The top is no doping. The bottom
Yes,
is with
see,
the manganese
this-
doping,
this,
which creates this extra
nice vivid
extra state.
green pretty feature is manganese doping.
with 2+, right?
Yes, with 2+. So with doping, with it is sextet, which means 5 unpaired spin. Everything looks great. There is no degeneracy, but closed shell with degenerate shows the. We do not know is it natural or it is artifact, but the degenerate states have very high rate of transitions between them. Probably it just go force and back, and smears out at the final state. But those high peak are between degenerate states.
Actually, how is your approach overall treating the degeneracy? Because usually you have really significant problems with degeneracy with surface hopping, for example.
There is no problems with degeneracy until 20 picoseconds. Then numerical problems appear. I'm hiding these numerical problems from this presentation, but I have movies that demonstrate it. Okay, so upon photoexcitation, electrons lose their energy into lattice vibration. Holes also lose energy in the lattice vibration. And how here is time and energy axis. But what if we look onto space? How the electronic state evolves in time.
Yeah, Jabed, we were talking about it, right? So can you make the same figures for your plates? Like same as Dmitry is showing now.
So it is a slice in the middle of quantum dot. You see it is cubic, as Maxim Kovalenko and Alexander Efros agree. And the yellowish and bluish parts are deviation from equilibrium. So
Like
the
blue is whole?
I will run it again.
So are the atoms
Blue.
moving?
No,
is it-
no.
It's
We can go up to nanoseconds or microseconds because we do not move atoms. It is decoupled motion of atoms and electron dynamics. So let's run it again.
just distribution of your. Were you excited initially?
So it is. Let's scroll back. Scroll back. So it is.
Excite here or
No,
here?
it is excite to the feature B,
Uh-huh.
and then it relaxes to the feature C.
Okay.
So then do you do a linear combination where the coefficients of population of the state?
Yes.
Okay.
Yes.
And it's at equilibrium jump.
Yes.
Once time starts pretty quickly, you get a distribution.
There is discussion. It is good.
John is.
He was online at the beginning, and then when he didn't saw you.
Aha.
And then, can I ask you another technical question?
Yes, please. We are here to just for discussion.
So this, we don't have a meeting, the ML meeting, so we
You
don't
don't?
have to leave.
You don't?
We don't. So yeah, it's gone, so we cancel it.
Yeah, so it's like a super.
But when you do this, you collapse each band into like just X and Y, and you add Z's, right? Like we did for your class.
No, here just slice. Not
So you just take the
There's no
slice.
integration.
Take
He
a
doesn't
slide.
integrate over X and
okay.
Y. He just taken really central.
So you just take like a
If you-
piece of
the
the
core.
If
right?
you integrate it, it will be a big mess. It will be just
All
mix of
everything.
yes.
Okay.
But am I right? So it starts here and then it's kind of move on to this.
Well, it is on.
Computational.
Next time on presentation, I will bring a Rubik cube because it has 27
Uh-huh.
elements, and this model has also 27 LEDs.
Nice. But
So it is only middle
Can
one.
I say that if you excite in a B peak, right?
Yes.
Then your excitation is somehow coming from this side.
No, it will be definitely compensated by other two slices.
It's symmetric, right?
It's if it migrates to one side, it is bad. It means it will be less optically efficient. It is
So you're saying it's still staying spread over the
spread.
entire thing.
There are some clear good things, and there are some things that are not yet clear. So the central atom, which is the only bulk LED atom, shows very clearly S5 or 6S, whatever is attributed to LED. This is good in what is expected. All H atoms show this more like D structure, but there is no D character at the
Can it be
band
just
edge.
as P?
Yes, it's likely the one PX has electron and PY has hole, and they coexist on the same
It's not
edge.
D.
It's not D. It's P orbitals of
And also
different
mixing
units.
with S probably as well.
Yes.
So going back to Svetlana's the question where she said this charge transfer, do you think that you have like you have layers and each layer starts out oppositely and they go like this?
I guess.
No, he's saying it's
No.
artifact because it's a slice. Like if you look on the other slice,
So what I'm
then
saying
you will
is
see it on
like
the.
your initial states are here. And your
Technically, it is possible, but if it happens, then all this is garbage.
But then
No. We assume that order of orbital indices do not change, and they perform this.
no, I'm saying
He's
like
talking
you
about
have,
in the space.
you,
in the
you
space.
you have
You go from top to bottom.
3 layers across, 3 layers back.
Yes,
So
one layer
one layer
in space
is
go
here,
up. Yes,
So it's
yes.
like this.
That in average the center of mass or center of charges stay in the center.
Okay.
I guess for this model, we do it just because it looks cool.
I have a technical
Like if
question.
you're doing charge transfer, you'd be able to see like blue move one way and orange move the other way.
So there's really no
It looks cool, and you know where your chargers end up.
like.
Like, when they realize.
But what if you just integrate over, in your case, period, right? So like, really look what's the contribution of your. Looks like your ligands do not contribute at all.
Yes, it is good result, except maybe a couple of oxygens here. But ligands make the job.
My
and
point
push
is
to-
like if you integrate not along X, Y, and Z, but probably over the period or like in a spherical coordinates,
Mhm.
right? And then we can clearly see whether you
like-
have
Yes.
like something what we
Like-
were
Yes.
trying to discuss with your core shell.
This would be
Kind of like this,
really,
yes.
It would be really cool if you would have spherical particles, but it is predominantly cubic.
But you could divide by the.
You can
the-
put cube inside the sphere.
Yes,
It's not a
but
problem.
on experiment, those are cubes.
No,
we-
no, but you still can integrate over the spherical.
Yeah.
So how do you model your propagation down for your electrons? So you
By density matrix equation of motion.
You just showed formulas. You didn't
They'll
get.
give you.
I'm kidding, of course.
It will get much longer time.
so I mean you force your excitation the same way we
We
did in
can
class,
create
right?
like
Early,
you.
right?
Just a second.
No.
You said you expecting that someone will be presenting kind of a lecture
Yes. Yes.
on a
Methods.
how you call it
Methods.
density matrix
Correct.
red field
Field.
theory, right?
Yes.
So You do know who, Erin?
It will be collective. It will be spread.
So sometime in July, just join.
In-
We'll go
in couple of
in
weeks.
a really kind of like a lecture style. This
What is
methodology.
plug here is for delta.
Yes.
Delta.
Do you know how Charlie's
So that means
which
is
is
the
happening
difference of the
Only during breakthrough.
local difference of the charge at the next state and the previous
We achieved the goal.
This is the
They
difference.
now
Inspired.
They now are kind of in a discussion.
I think except maybe you.
And that is the
He has an assignment to complete.
And who is hiding
Oh.
there in a corner?
Ben?
Ah,
Who's
okay.
Ryan?
Who's Ben? Ben, show your face. We cannot see you. Hi Ben. Here is Ben. He's undergraduate student.
At NDSU?
Uh-huh.
Oh.
Okay, I think we had enough discussion. No?
Consider just one.
They're good by themselves.
So is all blue is
What
the
year is
difference
that?
of the density of whole.
What
Benjamin.
year?
Benjamin. Oh, but he is third year, I think. He was taking my PChem class.
Okay, let me suggest that next time someone else will generate similar movie and we'll continue discussion. And there is another result by Aaron.
This is the difference of correlated results.
Guys, are you done?
Let,
Maybe
let's complete and give floor to Daniel because he
You
also
didn't talk yet?
no he has something to tell.
I thought we missed him.
No, he didn't miss most.
Oh, he has to get his second year seminar going.
Next year, yeah.
Not-
Oh wait, no, is he? Yeah, he's chemistry. Can I throw this one?
Okay, so if one looks,
I was gonna say.
so if you follow the excited and non-excited states over time and multiply by oscillator strengths, one can get time-dependent luminescence, and if one integrate over all times, there will be steady-state emission. And here is the comparison of this closed shell undoped and doped system. Well, it was expected that doped will be much better emitter, but in this calculation, the undoped is.
And you know why?
better.
Because you have not right electronic position of this D state.
Yes, we do.
It's supposed to be inside the gap, and you have it in the well.
One is expected to have good results with hybrid functional.
And this was not.
PBE without hybrid goes for like a month. Originally, with optimization. When it is optimized, it is a little better. But
The good story about hybrid functions, you don't need to optimize with hybrid
yes,
functions.
you cannot
You just
optimize
run
hybrid.
single point calculation.
So it is a summary, and those are transitional metal states that are assumed to do this orange emission. And here is the credit to some people in the. Yeah, I need to update this one. Okay, and
Oh.
No?
There was a big delay period.
so
We're moving to Daniel.
yes. So Daniel, would you like to come up and present?
But he will say no.
Yeah.
And you do not need to show because your slides are already on the screen. Just tell me when to change. Aaron, can you please focus camera on Daniel so that we see how he speaks? No.
No.
It is. It's cool, but there is buttons. Try the number 1, number 2, and which one will work better. It will swap between yes, and now focus.
Oh, that,
Okay.
Okay,
My work.
there,
Excellent.
There, yes.
that's perfect.
Also, he's done.
So basically, it's just a continuation of what I've been doing so far. More of a, I sort of kind of need a couple of I guess what is it called, advice a little bit because it took me a little while to understand how Edison was working. So if you can move on a little bit, please, on to the next slide. I'll talk to you a bit about what my presentation is about. So yeah, I guess a couple of little new results I've done, a couple of difficulties, some that I've overcome, and some kind of need a little bit of help. And obviously the goals, because there should always be an end game to anything you ever do. And I guess a couple of papers to help me understand what I'm talking about a little bit. You can skip to the next slide, please. The next couple ones, I guess.
Next one.
Next.
So he cannot move by himself?
No, I'm
Otherwise,
projecting.
we don't see it. On this.
So I guess a critical piece of information that I was missing whenever I presented this about a month ago were binding energies. I had a hard time trying to figure out how it worked, but I guess after seeing you talk about it for a little bit, I got an idea of how it should be done. So basically what I did was I took the energy of my completed perovskite, which in this case it's a slab of a 2D perovskite model with the ligands of ethyl ammonium and acetate ion, with subtracting by the total energy of the slab, and I guess the energy of the two ligands.
Daniel?
With that,
Daniel?
Yeah.
A complete perovskite, you mean the slab plus ligands?
Yeah, the slab with the two ligands on it. I guess I didn't really know how to put it, so I just called it the complete perovskite.
And we have question here, why there are two ligands? Can you explain it?
Why not 5?
Why not?
Why is there two ligands?
Yes.
Well, I guess I didn't include really the initial data from when I presented it. Whenever I did a density states, the acetate ion bonded onto the slab, I found out that it's a suitable P ligand, a P-type ligand, while the ethyl ammonium is a N-type ligand, which together they can form a PN junction semiconductor, and I guess with that it facilitates charge transfer. And
Daniel, can I add something?
Just with where?
yeah, of course.
So you have P-N junction. If your P and N dopants are separated far in space, if they have high concentration and they are intermixed, if they are not far, if they close in space, it brings you back to the intrinsic semiconductor that doesn't have charge transfer. But for us, it is good. So for charge transfer, one would need additional layer of another material or much bigger slab of perovskite. We are reproducing intrinsic perovskite due to simultaneous doping, but by P and N species.
So your
Okay.
ligands are the dopant?
Right now I'm just serving on behalf of Daniel. His discovery was that if ligands are attached not together, not two ligands but only one, they serve either as P dopant or N dopant, which is easy to understand since
Because
they
it
are
charges system.
charged, anion and cation. I'm done. Daniel, please continue.
But he just like these two ligands is enough to compensate the dangling bonds, or what exactly is the purpose of these ligands?
Daniel, can you try answering this question?
I'm sorry, I didn't hear the question that well. What was it?
So do you have dangling bonds on the surface, and you need ligands to like same as story about the quantum dot, right? So you need ligands kind of to get rid of your dangling bonds on the surface. Is it the same here for the 2D structure for the surface?
Well, I guess really, kind of not really. It's sort of from I guess whenever I took the image from I really should have included that information, but what we saw was we saw a bunch of charge transfer between the surface and these two ligands. Typically around the home orbital, there was a lot of transfer between those two, and that's where a lot of the energy was at. There was
Okay, then Daniel, can I contribute and then you continue? So answering the question,
Yeah.
is two ligands sufficient to compensate for potential dangling bonds? No. One needs the amount to cover, to have the complete monolayer coverage. For this model, it would need, I do not see it from here, but something like 4 anions and 4 cations on the top, and 4 anions and 4 cations on the bottom, to have both to cover the slab from everywhere where it interfaces vacuum.
Then, why you use only 2?
Why Daniel uses only 2? Because one needs to start from something simple. As after he will learn mechanics of binding of 2 ligands, he will process with covering 100% top and bottom.
So,
Daniel, am I right?
Yes.
Good.
So I have another question. It appears from. Oh wait, Javed, are you talking? No.
Yeah, I have a few simple questions there about how did you calculate the binding energies? It look like this number is too big.
It's less.
I checked it.
Oh,
Only last number
which
is
units?
binding.
Electron volts?
Yes.
No, but it's 10 to 0.2 times 10.
No. It's total energy.
It's
Oh,
he did
total
subtract.
energy.
This is always a binding.
He shows us primarily.
But this is total.
Like
Okay.
A plus B plus C equal D.
But this is total energy bind. He has 2 different ligands. Binding energy to which of them?
No, I think.
He should be able to answer this. Daniel, can you answer?
Yes.
Good.
I found out the binding energy.
Yeah, what's the binding energy?
The free energy from the alpha file.
I mean, there are 2 different binding. She asking that we have 2 different ligands.
Yes.
Is the binding energy of which ligands?
The ligands category. From this simulation. From the third simulation, I guess the third image, right?
So this ligand energy is the total energy of both.
Of both.
Of the acetate ion and the ethyl ammonium ion. Yeah.
So it is not single.
No.
Daniel, may I ask? Daniel? Hello?
Yeah.
What would happen if you remove only one? What will be the binding energy? Will it be bigger or smaller than removing 2?
Bigger.
If I remove one ligand from the structure, from the overall structure.
Yes.
Or just
Yes.
No.
If you remove one from the overall structure.
It should probably, when I looked it up when I was doing it for the class, I think it reduced the energy of the complete perovskite to about 0.17. It reduced it to basically about half one.
No. Please tell not the total energies, but binding energy. What is the binding energy of removing one ligand? Is it bigger or smaller than binding energy of removing 2 ligands?
I believe it was less. If I removed one, it got weaker.
But if you just take 1 by 1, right? Then technically, what you look on a binding energy of 1 charged ligand, let's say negatively charged, right? And or the second case would be positively charged. And here you kind of have neutral case because your positive and negative together balance each other. So it looks like intuitively you expect that the charged species should interact strongly.
But from his images, it appears that he computed the ligands in a single box. So then you could have charge interaction between the ligands, which then would decrease the ligands, which then would increase the overall.
Yes. What you are telling, what she's telling, what I'm
We all
telling, we
correct.
all agree.
Yes.
And it disagree with what.
No, but if that's the case where the ligands binding, the ligands
Well,
total
it's an
energy
interplay.
decrease,
Of several effects.
and the other ones.
No, decrease, not in like absolute value.
I'm saying if you take his box that say ligands, that should.
No. Just think only on the bottom left
Yes.
and remove only carboxylic ligand and compute binding energy according to your standard procedures.
Yeah.
What is expected to be like minus 7 instead of -8 or -20 instead of -8?
I guess yes. The absolute value gets larger.
Yeah, it will be more.
Negative.
Yeah,
Like
because it
minus
will
20.
be additional coulombic energy
Mhm.
of the attraction between these two ligands, because they are charged species.
Unless the influence of the surface decreases the interplay between them, and when you take them out, then they can only interact with themselves, which then would make the interaction stronger for the independent ligands.
But they
versus-
do interact between themselves even on a surface.
It is very interesting, and if you're right, you can make single author like ACS Nano on this.
I'm not saying you would have to look at the calculations, right? And I don't have them.
My
Well-
history calculation is wrong, I guess. This number is.
No,
That's a
but
great comment. Everything is wrong.
if you divide it by 2, then it's around 4, and I've seen charged species around -4 binding energy.
We have seen -12.
Yes.
If we have
Alisa,
these three
also
numbers,
see.
it's going to be around 1 point something. If we put these three numbers in the equation, it's become like 1 point something. It's not a negative.
Okay,
What-
I'm gonna do the math right now.
I would say yeah.
It might be units also issue. I'm not sure that. I doubt that this is. Well, it's VASP, then maybe it's electron volts again.
Okay, let's continue. Daniel, please keep telling the story.
I guess this is slide number 1, number 2.
Yeah, I guess if I guess I'm getting challenged a little bit by my math, but I think I
But-
did the math correctly.
But just to finalize, like since we had so many discussions and questions, what happens? Why not really calculate the binding energy of a single ligand?
Or maybe just show it on slide next time if you
And
have
then compare.
computed in the past.
Right.
Yeah, okay, I can work on that. Well, everything worked out together. I guess I got the total binding energy of
You get minus eight?
-8.74 electron volts. Thinking literature values about -12, but it's something that I gotta work on a little bit better. But that's because I'll talk about that later. But if there's a little more discussion on this slide, we can move on to the next one.
Okay.
Nobody has any more questions on it. So, yeah, one of the main problems to this, I guess, that I could try to get more accurate results is my periodic condition settings, I guess. It's something that I'm having a little bit of trouble working on. But I guess Yoon told me something about Vesta, so it's a program that he said will help me out with the initial boundary conditions when it comes to inputting files into Vesta. So it's something that I guess I'll look into, see if it'll help me out. And I guess I had a question. I guess somebody from the group can.
But Daniel, what is the problem with periodic conditions? So why are you unhappy with it?
I guess one of my initial settings, whenever Yoon was speaking to me about my project, he told me what kind of structure it was. He told me it was about a 2D structure. Then he asked me if I had a vacuum on the z-axis, and I told him not really. I think my initial condition had the z-axis at around like 21 angstroms, I believe, and so I guess it should be closer to 0.
What?
Since I guess it is a 2D structure.
What? Close to zero? What it should be close to zero? Why do you need the vacuum layer? Why do you need the vacuum layer on your z direction? What if you really don't put your vacuum layer? What would be the difference in this case?
Because I guess I'm working with a two-dimensional thin film.
Okay.
So I believe that it should be a 0 on the z-axis. It should be a vacuum, right?
Zero vacuum?
I think he means between the atoms, it should be 0.
Zero what? Angstroms? Which unit 0?
Let me show. If everyone supports, I will temporarily stop this presentation and show one figure
But
that will help our overall discussion. No. We have problem with the concept of periodic boundary
I think
conditions.
it's already shown back with the binding energy model.
No. Let me show something.
But Daniel, again, why do you really need this vacuum layer? How do you understand this vacuum layer? By your words, why do you need it? What is it? And what happens if you don't have it?
Well, essentially, I just believe that I sort of do believe because it's a two-dimensional thin film. So the fact that it means two-dimensional, right? There should only be two axes in it. Well, two axes, yeah.
So technically, when you put your 20 angstrom, like in your cell, right, kind of vacuum, it means that after 20 angstrom, you have a periodically repeating system. But your 20 angstrom, it's 2 nanometers, right, 20 angstrom. At this distance, you expect that interaction between your images should be really negligible. So they will not really interact. And then if you have such a huge vacuum, your periodic boundary conditions do not make any bad things at all. So technically it should be opposite. The bigger the vacuum, the more accurate calculations would be. Because if your vacuum layer will be small, it means you your replica along Z, right, will be interacting with your initial cell. And then it's not really a two-dimensional plate anymore.
Yulun, may I have your permission to show your figures?
Yes, go ahead.
Yeah, thank you. So those are figures prepared by Dr. Han, and they are on a similar nature of, similar ideas of computing binding energies of different molecules to perovskite surface. So what is important in these figures that they show not only, do you see my mouse? Yes, I see my mouse myself. So panel A. So it shows not only the model, but also the periodic box. So those atoms which are inside periodic box are actually modeled and mentioned in the postcard file. Those that outside, they belong to periodic replica. So there are like 2 lead ions, and the third one belongs to replica, right? And there is a vacuum like between this carbon dioxide until letter A, and then this space is a vacuum. And then if you go further up, we will reappear at the bottom and smash into the replica of the slab. So Daniel, when you present, please try to show size, to explicitly show your periodic box.
Yeah,
so that we can immediately understand if there are problems with sizes, with adjustment of vacuum and such.
Now, look, like if this z-axis will be decreasing in size, right? It means that your replica will start interact with your molecules from the first cell, and then it's not.
Yeah.
And then it's not good. So technically, the bigger your vacuum layer, like if you can do 30, 50 angstrom, the better.
Okay.
So you don't want to have 0 for vacuum layer. You want to have it as big as possible.
It's just technically too expensive to have it as big as
right.
possible. And if you take more than 10 angstrom vacuum, everything will converge and stop changing. But there will be nothing wrong to put 100, other than the job will run for a year or whatever, 2 months. Let's go back to presentation by Daniel. Okay, please continue your story.
We completely disagree that you have any problems with your periodic conditions. If you really can create the 20 angstrom vacuum layer along your z direction, then you are okay. Everything should be great.
All right, then, yeah. That was just one of my questions, I guess. I'm still kind of trying to understand periodic conditions and I guess that's kind of like the most important thing running fast. But I guess it's just something I'll pick up really quickly along the way. But I guess another question I had was whenever I run something in Edison, I guess I get alcohol, but I guess they use a slur to control how jobs get submitted and stuff like that. So I guess I read this in the output file. So I guess whenever that happens, I guess it converts, right? I mean, basically the job finished. I don't gotta worry about it. And I guess so. Essentially, if I don't get that or if I get hurt, I can just copy the COM cards of pulse card files, and just you copy the files and continue the job, right?
Yes, yes, it is very healthy approach.
Alright, yeah. So I guess that's it for the difficulties. I'll just move on, try to figure out periodic conditions, and well, play around with best stuff since I got a nice recommendation on that program. Come on to the next slide. Yeah, so I guess sort of my goals before the end of summer is to be able to try to determine if there are any state trap states formed in this complex with these specific ligands. Determine if these ligands are making decent PN semiconductor. Determine the efficiency of charge transfer with these two ligands.
Do we have
Obviously,
states
model
without
the molecular
ligands, just by
dynamics
the
of
surface,
these
due
structure
to
now
the
that I got
surface
enough time.
reconstruction?
And I guess the
Probably
big
is the first question we need to
topic
address.
that'll probably help me out for the rest of my future projects too is understand periodic boundaries, since that's a really key topic to figure out. If there's any questions on those, move on to the next slide. List of any comments.
No, before next slide, we will have comments. We just have internal discussion for 10 seconds.
So technically you said in the very first sentence, right? So you wanted to see whether you will have a trap state due to the ligand, right? But
Yeah.
even if you have no ligands at all, right? Your surface, due to the surface reconstruction, because again it's lacking the atoms which should be in a bulk structure. So this surface reconstruction or this surface defects might lead to the trap states as well. So I would say you probably need to check that you don't have trap states due to the surface, and then maybe look on your ligands. Or you're 100% sure that there should not be any surface states due to the surface if you have just a bare surface.
So, Daniel, can I start answering this question for you?
Maybe Daniel can answer this question.
Therefore, I'm asking his permission.
Question again, I apologize.
The question is,
What was the question?
are you expecting that there will be trap states just due to the surface, even if you don't have ligands?
I wouldn't really think so. It's just, well, I guess without the ligands, then it'd just be your ordinary perovskite structure with just your cesium, your lead.
Well, perovskites are three-dimensional materials. They are in the bulk, right? Bulk means you have neighbors in all three directions. Now you have neighbors only in two directions, and one direction on the surface lacking the neighbors. So you create a dangling bonds. You really breaking a bond. It's not enough, like your atoms changing the coordination. If this happens, dangling bonds results on trap states.
So lead atoms on a surface. Lead atoms on a surface, instead of being 6 coordinated, they become 5 coordinated. It may have some chemical consequences. And the question of Professor Kivina is whether the 5 coordinated leads will bring to formation of trap states.
And Daniel's answer is no. What is your answer? Yes or no?
So the question is not yes or no, but how to check the answer. Where to get the answer from numerical calculation.
Just take out ligands and calculate.
Not calculate. Which form of analysis Daniel must commit?
Absorption or DOS? Very little.
No, very little, but next step. Just look on the orbitals.
Yeah.
So
We need to calculate.
Calculate first.
Calculate? He said, no, we should not calculate.
We all need to calculate, but then you need to visualize, interpret and visualize some observable. So, Daniel, you do need to plot orbitals.
Not those, or projected.
No, orbitals. Orbitals first. To primarily first to see whether there are trap states. If you have image of an orbital, how would you discriminate between trap and no trap? What's the difference in the shape of orbital?
Well, I guess The trap state in the dots. What if there's
No, not DOS. Plot of orbital partial charge density in space.
Yeah. Okay. How would that? How would trap state look like? Just the orbitals plotted?
Yes,
They look like clouds.
but where these clouds are localized for normal intrinsic state of perovskite and for trap.
They'd be localized on the surface?
Yes. So you need to check whether your HOMO and LUMO for a model without doping would be distributed evenly over the whole slab or localized on the surface.
Or maybe just on a specific atom, also possible.
Yep.
If it's a defective one.
It's critically important analysis. Would you agree to try this?
As you
Yeah.
say.
Okay.
Absolutely.
Okay. Thank you. I want to answer something to Professor Kivina.
I already
No.
satisfied with the answer.
I'm not satisfied with the answer. Even if the analysis that Daniel plans to do will show no trap states, it will be only for equilibrium geometry. But surface traps may form during molecular dynamics. Therefore, we need to set up some measures against it. One thing. Okay? And now I have a comment to Daniel. In your list of goals, you are missing two things that you can add. First, to make full coverage, like 5 anions and 5 cations on each side. This is and it is very doable before the end of the summer. And second, try to use equations for particle in the box to reproduce shape of orbitals and energies. There is a guarantee.
Two-dimensional.
There is a guarantee that it will work for this system, and the guarantee is provided by Dr. Efros from Naval Research Laboratory and his Nature paper. You also may find this paper, read and present on the meeting.
Yeah.
Okay. Do you have more slides to go over?
I guess just a couple of research papers, I guess,
Okay.
about it, but they're not really papers, but I guess a couple of topics I kind of want to get down before the end of the summer.
Okay. Should we go forward?
Yeah, it should be the last one. Yeah, so I guess a couple of papers that I kind of want to know is how to understand trap states, how people in the field, I guess, model, present trap states, how they work. I guess everything about them, essentially, then the mechanism behind charge transfers and perovskite systems, along with just understanding more about PN junction semiconductors. And I didn't really have time to pull up sort of papers that I found out and include it to the presentation, but I guess if anybody in the group has any type of papers that about these three topics, I'll appreciate it if they can give it to me. But that's about it, really. Just guess I want to learn about these three topics.
The group will try, but what would you do if no one sends you papers? Where would you find them yourself?
I already have some about these topics. I was just trying to see if anybody else has some. I have a couple papers on how charge transfers work by I think the name is Mike Pretzel.
Good, good.
And yes, also I was just gonna look up see how trap states work, and because that's sort of something I'm not too familiar with myself. But I guess after reading a couple papers, I should be able to get the main idea out of it.
Okay.
So, how is your research going to address PN junctions? Because I thought Dimitri already said that you have to be spatially separated. Your P and N have to be spatially separate to get band bending for the PN junction to actually work.
Yeah, then I guess that was something else I wanted to add to my goals, because currently right now I wanted to see, well, when I ran this, how the model is right now during class. I saw that I thought there was some type of hydrogen bonding going on between my two ligands. I wanted to see what happened. I guess I separate it a little bit further than what it currently is at about like a few angstroms. I want to see if I guess I could just play around with them and see how they interact around the surface if I make them further from each other.
Daniel, can I contribute to your answer to Levi?
Yeah.
Okay, so if Daniel or someone else would really like to develop this project towards PN junction as a quick test, one can put one ligand on one side, another on another side. And then for the excitation, we'll predominantly lead to separation of charges.
Band bending would be along the...
Yes.
Okay.
And this could be a fun test project, but it is not the main goal.
But then isn't the PN junction, the PN comes from the nature of the ligands.
Yes.
Here,
So then,
well, it is not common knowledge of the community.
yes.
It is a discovery of Daniel that suddenly one can, the ligands are equivalent to doping. Surface.
So then,
However, again, you're probably not expecting that you will have just a single ligand on the surface, right?
yes.
And if
but
you have many of them and all are negatively charged, then again,
Yes.
you're not expecting that they all will be sitting in a
So
one
then-
layer.
then he needs to find 4 different ligands, 2 that are oppositely charged that are P, 2 that are N, so that you can have,
Is it 4 different, 2 different?
no, because you need positive and negative on each side, but you need both P
No,
on
yeah,
both
wait.
N.
Too complicated. No.
But otherwise,
we should-
if you try and do N on this side, P on this side, to make
in
the
fabrication, one can prepare top and bottom with different treatment. One can make a gradient, but it is not the goal here.
okay. But then if you
The standard thing is what Aaron did a year and a half ago, and what London is doing, hopefully doing right now.
Where's London?
But the thing is still, if you try and do P and N,
For perovskite, you don't do PM. You do titanium dioxide for electrons and spirometer for holes.
yes, but if his premise is saying use these ligands for PN, then
Well, maybe we are on the threshold of a great discovery.
okay.
But it is unusual, and if it is
So,
true, it will be very
I
novel.
would say this goal is more like educational, right? So he just
Okay.
wanted to educate himself what is a PN junction.
Daniel, thank you for permitting me to represent your interest in front of Levi.
Yeah, of course. But I
Are we
guess that's
done?
about it. Go ahead.
Brandon has a question.
Great.
So you didn't show anything about putting these 2 ligands on all, how many sites? 4 different sites? 5 different sites? So how does the binding energy compare just depending on these 2 where you put them?
He should calculate it.
I guess I sort of just put them on what I believe would just be the overall surface, since CCM atoms are usually located in the middle of the structure. So I guess I didn't really, I believe they would just be attached to the outside, which is just the lead and the iodide. Or the lead and the bromine, I apologize.
So
that's
let's.
something that really comes to my mind. Go ahead.
I do not have the answer, but I have a hypothesis that you may try, and then it may work. So that maybe there are so much preferred absorption sites for anion and cation. So no matter where you initially put it, it will, through optimization, it will find correct site. Because it is main result from what Dr. Han recently did in studying molecular adsorption, that if one has anions and cations, they will find a spot where previously natural anions and cations were sitting to maintain crystalline symmetry. And those, because of symmetry of electrostatic attraction from other anions and cations, it will be so much more preferred than any other interstitial or whatever sites.
So you're saying like because of the symmetry and because of your nature of your other pieces of your perovskite itself, right? So not all 5 sites will be exactly identical. you will have maybe really a few sites which may be differential due to the symmetry reason and this, let's say, dipole moment for the charge.
Yes. For charged ligands, there will be
Limited number of sites.
yes. For uncharged, like what Dr. Han faced recently for like carbon dioxide, there are several sites which are almost equivalent. But if one gets to charged species, it is very well determined.
And he was choosing this spot for his ligands already based on this previous knowledge of Dr. Han, who is it?
Yulun?
Yulun?
Daniel, can I scroll back to your geometries?
Yeah.
Oh, he just put it randomly.
So let's look here. Well, ask Daniel where he put it. But if you look on the geometry here, then this carboxylic group, anion, is right above of this gray lead cation. So it complements it from 5 coordinated to full octahedral. And this cation of ethyl ammonium is staying approximately the same place where this purple spheres of
Iodine or bromine.
cesium.
Cesium.
Cesium. So
So you have lead and cesium.
yes, lead is cesium. Lead is 2+, cesium is 1+.
Red is oxygen, or
No, it's bromine.
Bright red is oxygen and dark red is bromine. So whatever you were discussing is supported by images from Daniel's calculations.
bromine doesn't get passivated if it's on the surface.
No, it is, right?
Well,
It will be passivated by this positively charged ion.
it is not coordinated, but it is passivated by being in the nearby same vicinity, same as cesium cation here. It is not literally coordinated to any of the 12 bromines that are nearby.
So it just makes like a field, and it's happy with that.
Yes, and some chemical chemists, or synthetic chemists, may tell that it is similar to ionic liquids.
Okay.
Or so it
But
is.
for lead, it is coordinated.
For lead, it is coordinated. Yes. Daniel, you do not protest. Do I represented you well?
Yeah.
Okay.
You did good.
He trusts you.
Okay, so let's go to your literature. Are there more slides to go forward?
No, that should be the last one.
Acknowledge.
Let's check. Yeah. Okay, let's thank Daniel.
Good.
Now let's check if anyone has comments or important things to discuss in Los Alamos or in Fargo or in communication.
We have discussed already.
Before we leave, if I could talk to Svetlana, that would be great.
Okay. Anyone else?
I've got like 2 questions. But
Good. Aaron,
Yeah.
can you please focus back on the class so that if there will be one-to-one discussions, yeah, and maybe zoom out. Okay, excellent. So, anyone except Alyssa needs more discussion? More discussions, one? More discussions,
Oh, I
two?
do have a question to Robert Jabet. Was the Gaussian VAS problem solved or not? Like, can you run VAS or not on CCAS?
Yeah, but now I'm able to run in the phase 1, login 1. But Neo 1 is still, we didn't get any response from the Neo 1.
I tried to log
Oh. And in your old one, how many nodes are available?
in. I think that's what's
They have 13 nodes.
Huh. Okay. So it's definitely much less than for the rest
Yeah.
of the cluster.
Yeah.
Okay. But did they answer to your email or they didn't answer at all?
No, he answered and Deep said that he's working on that.
Ah, okay.
They have to.
So maybe we will wait for another week and see what's going on. Okay, good.
Okay, if there are no more questions, let's thank all participants for discussions. And meeting is dismissed.
Yeah, but Alisa can ask you your questions. The other people.
Yeah, we'll stay online specifically for Alisa.
Okay, thank you. So my only thing is, I was looking at that paper for the acetate, for the quantum dots, because I was trying to do that new research, and I didn't know if you wanted me to do like the bridging types, where like I space it out over two sulfurs.
Well,
I can't remember which one
it is expected that bridging is the most stable structure, right? So that's why probably it's a good idea to start with the bridging, and then maybe we can create some other structures later.
One line.
Wait, so do bridging, and then do you want me to do both cadmium enriched and non-cadmium enriched?
Yes. And actually, we just discussed it with our experimental collaborator here, so kind of the mechanism. So we probably might think about that, like again, so the idea is that they can create these structures in two different ways. One way is they use a precursors of cadmium and sulfide, just like a solid powder, right? And then add the solvents, like amines or propylamine or something like this, right? Then add the alleic acid, which is passivated in the surface. And this would be one type of quantum dots, cat sulfide quantum dots passivated with alleic acid. So for these cases, it is believed that these structures has to be non-stoichiometric, and they have to be cadmium enriched to balance the charge of because alleic acid will be returned to the alliates, right? Because will be deprotonated. And it's believed that deprotonation is happening some way in the solution through the solvent, through the amines. So when it's attached to the surface, it's already negative anion, pretty much the same as Daniel was and Dmitry were discussing for their structures today, right? So in this case, the quantum yield of these quantum dots is not as great. It is, they're shining, but not really very bright, right? Another way how they prepare it with using the sials as a precursor. So not a solid sulfur, but sials which are providing the sulfur for constructing the quantum dot, right? So in this case, and they still have alleic acid, and they still have amines. So now they have three species there. So technically, in this case, we think that what might happen is that deprotonation of alleic acid can happen through the sials. Technically, the sial should be deprotonated with a proton going to the surface, right? And then it's deprotonating the carboxylic acid. And the proton might be going to the solution or might stay on the surface as well. In this case, we believe that the surface would be will be stoichiometric. We'll have same amount of cadmium and sulfides, right? And the charge will be balanced by these protons staying on the surface. So, and maybe in this case, the emission will be much brighter comparing to the first type of quantum dots, right? So that's why we need to do non-stoichiometric and stoichiometric. With stoichiometric, it's easy because you just put in your neighboring guys, right? Kind of sharing a proton, balancing the charges. Maybe you need two protons, or you can put one proton staying on a sial group, right? So it's still sial, right? Another proton is from carboxylic acid being on the surface, right? And they kind of sharing it and see how this will be affecting absorption spectra. Or you can really put these protons far away from each other, right? So many conformations can be done, but with a 33 structure, I think it's pretty straightforward what you do, right?
Yeah.
You just put two guys, right, and just then the question is what to do with their protons, how you deprotonate it, right? So and then again you can put a dicer in between them, at least one, right, and another on the surface. Or you completely deprotonate, right, and then make a charge and see if maybe charge system still will be bright or something like this. But if you create the cadmium enriched surface, right, then it's of course a question where to put cadmium, how to make this, how many cadmiums to put, where to put them. Honestly, we don't have the question, right? So how Levi was doing it, he was putting, how did you do it for your cadmium enriched surface?
So if I only had a single enriched, like 34 to 33, I put it on each layer
By one.
by one.
So getting 37.
No. So if I only put an additional cadmium, I put one on one simulation, another.
So
then
not 4 together, but just
Yeah.
one by one.
But then when I did,
That's what I did start doing.
yeah, then when I did 4, I started at one side on A, and then I kind of did a spiral down to D, because I assumed that the cadmium did not want to be next to each other because of Coulombic repulsion or dipole interaction. So that's why I kind of spread it as far out as possible. Another way that we could do it is, do you have bulk structure?
Yeah.
So
Yeah, I do.
if you start with the bulk quantum dot, right, you can see where each cadmium, if you added a single one away from the sulfur, would land. So then you could add randomly around the surface for enriching from bulk material and not from an optimized one. And that you might be able to, huh?
No, that makes sense. That makes sense.
Yeah. And on that, you might say, we want to coordinate sulfur that have 2 coordination, or because 2 coordination should be more reactive than 3 coordination. Yes?
Yeah. So then, for any of the bridging, like, do you want me to look at different layers, that kind of thing, like bridging between different layers, or do you want me to do only bridging on a particular layer?
Well, again, initially probably can start with a particular layer, and again, our assumption is that your A layer is the most reactive, right? But again, just to see what we see, like whether something is interesting or reasonable. But potentially, of course, we probably need to prove that it's not just a fluctuation, that we have whatever we see, whatever our observables, right? That how much they really will be changing if you put these groups in the other layer. So this is kind of a question, but I would say we probably can ask this question a little bit later. Let's start with some structures in the beginning, the simplest one, right? Get something to the absorption spectra, see whether we see any effects, right? And then we will either go with putting it on a different location, I mean, kind of in the same way, but just putting on the different layers, or we create completely new structures, right? But I think let's do it step by step. Don't because of course you can create millions of structures, but then I think it would be very hard to figure out what's going on after you really run all this million of calculations, right? So let's do it step by step. So start with a few structures, non-stoichiometric, kind of according to the idea how Levi was suggesting, right? And stoichiometric structure with nearest neighbors, kind of balancing the charge with protonating the surface, or really charging and losing one proton and charging the system and see how much is it really changing.
Okay, and then I just have one more thing. Do you want me to try like cascading it with like 18 amines or however many, like, you know, instead of 21 and do?
You know, because we were how many papers? Well, I mean, it's a very simple question which each reviewer likes to ask. Like if you start with a bare structure where you have just a single ligand, right? They immediately say how feasible, how really real your structure, because in reality the surface should be passivated with ligands. You're not expecting it to be the bare surface with a single ligand, right?
Daniel, do you hear this discussion?
So that's why
same related to your project.
Right. And I mean, like we were publishing many papers. It's always at least one or sometimes more than one. Reviewers will definitely ask this question if you're not passivating the surface with other ligands, right? So that's why, again, the suggestion is, as a first step, we start with a bare structure, like having 2 ligands or how many, or maybe 3 ligands, 4 ligands. But again, if we get in something reasonable, of course, it would make sense to passivate the other sides with amines, or maybe carboxylic groups, or whatever we decide, like whatever the majority of these guys would be. And again, hope that the results are not affected after you add in the other species there on the surface.
And another computational trick to get around weighting in the optimization is we know that A and C are the most energetically favorable for the amine to bind.
2 coordinated cadmiums,
Yes.
right? In these layers.
So then you could coordinate all 2 coordinated cadmium,
right.
which then you only have up to 9 ligands plus whatever's on the surface. So then you could have like
Okay, that makes sense too.
12 ligands on the surface.
Yeah. And again, for reviewers, this probably will be good enough to say, well, we passivate the most reactive sites.
Okay, perfect. Yeah, I'll do that, and I'll try one with both activations, see if it makes a difference. Alright, I just wanted to make sure I was like in the right direction, because I didn't want to do a bunch of work. And then
Well,
like,
but at least in this case, we don't have a right direction, right? Because as I said, like there are so many ways how you create the structures. No one knows what direction to choose. So I guess it's just your intuition or whatever, your choice, random choice if you want to.
Okay. Alright, well that's all the questions I had. Besides that, yeah, that's it. So.
Okay, and I for both you and Ben, I got your time and efforts. So I actually already signed. Dmitry sent me by email it already. I just need to submit to send it to Charlene, right? So I probably will do it. If not, well, I probably will do it today, but she probably will get it sometime tomorrow.
Oh, you don't. It's not due till Friday, so that's good.
Don't tell her that.
Yeah, I better do it today anyway.
Do tomorrow.
Yeah. So and I also working on your on the files which you sent me, the most recent files from Friday, right? So I have several comments on your figures. I was hoping to finish it today, but again, not sure how much I can do it today. But again, so sometime tomorrow probably you will get some email from me with red comments in your files for suggestions what you have to change.
Okay, and then I finished that last figure for the binding energies depending on the basis sets, and there's no change. So.
But I need your figure, right? I still didn't see your figure in this.
Yeah.
Okay, send it to me. Don't forget.
No, the last calculation finished today, so I'll send it to you.
Okay. Oh, and the question, like, you remember your file, so do you have a computer to look on it very quickly, or can we? I don't know.
I don't have a computer.
We don't have
with me
a
right now.
You can approach the camera and show it to the camera. No, it's approach there.
What is it?
Well, I have this question before, but I also approach the camera.
Approach the camera and show it.
And then you can see up in the. Oh, it's kind of.
Okay, yeah.
So you remember this figure, right?
What's up? Yeah.
So we're talking about red lines here. Oh.
There's a large like period.
What do you want me to change about it? Like, do you want me to take away the absorption spectrum?
No. I'm not asking about changes. What I don't understand, and here is your newest figure, 7.
Yes.
So one of the structures from figure 7 has to be exactly the same as your structure on figure 6b, right?
Yeah, the one that's the same is the phthalate without the proton.
So the blue dashed line, I think.
Oh gosh. Sure.
Yeah.
I think it's blue. I think it's blue.
No, just a second. I don't care about blue. I'm talking about red.
Yes.
Okay.
And I think that your figure 7 should have phthalate with a proton on the surface.
It does, yeah.
It does. So then I don't understand why they're different. Because neither of the structures on your figure 7 having the low state being the brightest. Right? All structures have low state being weakly active. And then the next one might be bright. However, on your figure on 6 with a B, right? Looking on these red lines, they correspond to phthalate with H. They have to be either on A or B or C or D, right? So the structure should be one of those which you're showing on 7. But your low state, the lowest energetic state is the brightest one here. This is what I don't understand.
What I think is happening is that there's like a network created between it. So it's taking more of the dull states are from the phthalate without a proton instead of from the phthalate with a proton. If that makes sense.
No, because again, what exactly is the structure you're showing there? So you're showing the spectra. But then I want to know where exactly your ligands are placed. In which position? A, B, C, D? Which one? So put it in a caption.
Okay.
For all of them.
I'll just email you a copy of that. Okay, because I know what you're talking about. note, but I can't. I need to look at my figures.
I know you. I'm not asking the question right now. The answer right now. I'm just because it was in my previous email, right? You kind of answer. You said that I don't remember what you said, but you something said like, "No, I rechecked. Everything is correct," or something like this. But this cannot be correct because again, the structure in your 6 should be completely identical to those structures which you're showing on 7. At least one of them should be showing exactly the same spectra. And they disagree. So you're either not showing the right structure, or I don't know what's going on. Recheck it once again. And again, in your caption, please, for figure 6, clearly identify where the ligands are. Are they on the A layer, or B, or C, and so on?
I think it does it not say what layer they're on?
No.
It should be A.
It's good that it should be, but it doesn't tell anything in a caption.
Okay. Alright, I'll look at it.
Well, anyway, yeah, so I will send you the more comments on it, if not today, then tomorrow.
Okay, sounds good.
Okay? And for Ben, you, like Jabet said that you were able to get all your calculations for absorption spectra already, right? Did you?
Yeah.
So, and
Are
now
you sure that I have all the absorption stuff done?
Okay, but can you now plot absorption spectra?
Yeah, I've got it.
He prepared the whole file and we discussed it today about that. He calculated absorption spectra by using PV1 functional and V3D benzo.
But I think would be good if you like kind of after training, right? So just create your files, create the absorption spectra in comparison, whatever panels or whatever figures for your different functions or whatever you're using, right? And send me kind of a preliminary draft with your figures sometime by Thursday, so I can take a look and then we can go to the more detailed discussion next week when I return back. Good?
Okay.
I'm done.
Good. Anything else? Anyone wants to? Aaron, thank you for your emails. I saw them and new results. I just need to focus after we are done with meeting.
Okay. Do you see my other email?
I saw 2, but it was so intense discussion, so I better focus on emails later.
Okay.
Fatima,
One question.
just will you be able to present next week?
Yeah.
Okay, very good.
About what?
About key points. Yeah, Jabet, you want?
One question.
Yeah,
Yes,
go.
please.
The question is about the quantum work for band starting calculation on the dot. So just making sure that quantum nodes is same quantum nodes and die is with a different heavy metals only or different dots.
I didn't get the question. The quantum dot is the same quantum dot?
So yeah, Funk share the 5 output file and they have the same dot with a different
metals.
Metal atoms.
Yeah.
So that's the system. Yeah, okay.
I suggest take ruthenium because it was the most studied so far.
Oh, okay.
So you take the structure with ruthenium, right, and then just kind of put it further and further apart from where it is initially was placed.
Okay, yeah.
Make sense?
So he is thinking to increase the distance by 10%. We have 10, 20, and 40% like that.
Yeah. So like you can just slightly disturb the bond. Like the idea is like first you just slightly disturb the bond, and this distortion probably will be through the thermal motion, right? When you run dynamics, your bond is doing something like this, right? And the distortion will be kind of in the range of distortion at the room temperature of this bond, just by a little bit, maybe a couple percentage if you put it in a percentage, maybe around 5%, right? Maybe even less, 3%, and then put it whatever 10. And then really kind of put it really far away from a surface when the interaction is almost no really a real bond formation anymore, or real coordinated bond formation. So because again,
right now,
the idea is how the levels will be shifting, right? Because when they interact, so the change in the dipole moment in both systems, right? For quantum dots, the dipole moment increasing, the dipole moment of the die is decreasing when they interact, right? And that results that the die orbitals go down and the quantum dot orbitals goes up, right? And kind of that's why the occupied level, I don't know, can you see me or not? The occupied level is so deep inside the valence band for the receiving die. But if they're not interacting, then their levels are not so much different, right? So they're kind of aligned much closer to each other. So kind of we want to see really where this change happening at which distances.
Okay. Okay, and he's preparing now input file. I guess by tomorrow we can submit this job.
Great, yeah. So then would be something to discuss probably next week.
Okay.
So we done? Should we upload it?
Yeah, thank you.
So we done for today.
Okay, we are going offline.